streams, and predator-prey interactions with plankton under acidifying ocean conditions. After finishing up her undergrad, she came back to Alaska and has done a variety of fish-related work, including working for Sarah, working for the Six-Town Science Center on the Hatchery Wild Chum Interaction Project, working for Fish and Game here in Juneau, tagging juvenile coho, but kind of got tired of collecting data for other people and decided she wanted to advance her career and do a master's. So she's going to talk about that today. Tessa has been a real joy to work with. She's really bright and inquisitive. She's self-motivated. She's self-confident, but also with a nice combination of humbleness, which I appreciate, and she's just a lot of fun. She has a good sense of humor, doesn't take herself too seriously. We had the fortune to spend a couple of weeks together in Kamchatka, and so a lot of these pictures I'm showing you are from that time. Another thing about Tessa, she's a really good photographer. It was a little bit hard to come up with good pictures of her because she was the one behind the camera most of the time, taking photos. This is a really nice bear shot that she got. The rest are by less professional photographers, including my 6-year-old daughter. But one thing about Tessa is she's not necessarily the most adventurous person when it comes to food. I was her in a market in Elizabeth. Fried caviar.
Too salty? A little salty.
And I do recall one instance when we were eating dinner in one of the hotels there, and there were Russian police in the lobby because there had been an incident the night before. So we were trying to just really stay under the radar, and we were going to have chicken wings, and Tessa was so excited about chicken wings instead of pink salmon once again. She was going, chicken wings, chicken wings. Tessa, can you stop being so American right now? But we survived, and I think Tessa has survived the master's process, and she's going to tell you about it today. Let's see if we can get you over to your presentation. Okay.
All right, Brian, can you let me know if you can see the presentation?
Yeah, looks good.
Okay, great. Just get myself situated. Okay. So, thank you everyone that came out today. That wasn't Brian.
No, okay. He's the orange.
That's Ellen. Just going around. So yeah, I appreciate everyone coming out today. Some of my old bosses are here, Fish and Game, and a lot of family and friends. So it's really exciting. I'm going to be talking about the research I've been doing for the past few years, looking at how Asian pink and chum salmon abundance affect Western Alaska chum salmon growth in the Bering Sea. I'm going to start with my acknowledging my funding agency. So most of this project was funded by the PCCRC Pollock Conservation Cooperative Research Center, which was really great as a graduate student to have 2.5 solid years of funding. And then the latter part of this project was funded by the UAF Global Change Student Research Grant Competition. So thank you to my funders. I also want to thank the Alaska Department of Fish and Game, as well as NOAA. Both agencies provided me with scales to use in my analysis. And I just think there's a lot to be gained from this interagency collaboration. So thank you. I would also like to acknowledge a few people, my committee members, Drs. Megan McPhee, Milo Atkinson, Alan Yasumishi, and Brian Beckman. I received statistical input from Yashik Masoko and Dr. Franz Muter. Dr. Bev Egler and Dion Oxman at the Mark Tagan Age Lab provided me with scales that I'm using in the analysis. Lorna Wilson trained me how to read scales. Dave Nichols mounted scales. Evan Fritz made maps for me. And then I have to send a huge shout out to everyone that supported me throughout this process. Nathan Frost, my boyfriend, who flew back from the Taku to be here, and is still dating me. My family, my mom Phyllis and my cousin Tim, who know what they did. Pat Berry, who I share an office with, and as a result had to help me with a lot of code. And then the CPAW students, Lauren Wild surprised me this morning from Sitka. Then Maddie, Cheryl, Valentina, Doug, my friends Autumn, Julie, Katie, and Gabby and Chris, the whole McBee Lab, students and staff here. And then my dogs, Seda and Bear, who are not actually helpful, but we're distracting. So. All right, with that, I'm going to jump into it. So I'll be talking about two species of Pacific salmon today, quite in depth, and I want to point out a couple differences between the two. So chum salmon here on the right, I have both chum and pink in their spawning and ocean bright colors. Chum salmon exhibit variation in their age at maturity. So they spend 2 to 5 winters in the ocean before returning to spawn. The dominant age at which they return is after 3 and 4 years at sea. And then pink salmon, the big difference between them is that they have a very fixed 2-year life history, meaning they spend 1 winter at sea before returning to spawn. And those differences are going to come into play later in the analysis. So chum salmon are really widely distributed in their spawning range. They're found from as far west as Korea and Japan, throughout Russia, throughout western Alaska, the Aleutians, southeast Alaska. They do have limited spawning distribution in Washington. So they're found all throughout these areas. And what's going on with chum salmon? Why are we talking about them today? Well, throughout their range, so what I just showed you, their spawning distribution, chum salmon are experiencing decreases in fork length. This is looking at fork length at maturity, so when they spawn by brood year. And we see this pretty dramatic decrease in that average fork length around 1980. This is looking at a population from Japan. However, these trends have been seen throughout their range. And some populations did increase in fork length following that big decrease. However, they've never returned to their previous length. We've also seen decreases in growth. This is looking at growth in millimeters per year for the different ages. And what I really want to point out is that these lines going down through time, that's showing that chum salmon are decreasing in growth during certain years that they're in the ocean. So this is age 03, or age 3 and age 4 are experiencing large decreases in growth. And then they're also experiencing an increase in the age at which they mature. So this is age at maturity in years by brood year, and for both male and female chum salmon, we're seeing an increase in that average age at maturation. So because these changes are being observed throughout their spawning distribution, that leads us to believe that there's something happening, some kind of common variable that might be driving these changes. So I'll be looking at chum salmon from western Alaska. This is a very rough sketch of western Alaska, but you'll notice that it encompasses a lot of the state, about 40% of the state, and it includes the Yukon and Kuskokwim River and then the North Sound watersheds. In western Alaska, there's been pretty dramatic declines in the abundance of both Chinook and chum salmon. I'm showing you here the Yukon summer chum salmon harvest in thousands over time. This is just one population of chum salmon in western Alaska, but this pattern has been observed throughout the area. And what you can see is that the gray bars, those are showing commercial catches, and the white bars are showing subsistence catches. And around the late 90s, there's this really dramatic decrease in the abundance of chum salmon that led the Alaska Board of Fish to declare numerous fisheries disasters. And in western Alaska, commercial fishing provides sometimes the only source of monetary income, and subsistence catches are a really important source of food security for people, and even more so when the abundance of Chinook declines. So understanding what's driving these changes in abundance has important implications, but especially for the people living in this region. All right, so we saw that western Alaska wild chum are declining. Well, what's going on with other salmon? So this is looking at hatchery salmon releases from 1952 to 2016, where we have releases in billions over time. And hatchery production really started to gain momentum around 1970, kind of increased substantially from 1970 to 1990, and it's been relatively stable since then. These are the 5 species of Pacific salmon found here in North America, and you can see there's a lot of blue on there. That's showing hatchery chum salmon, and then pink, showing hatchery pink salmon. So the majority of this figure is blue, meaning that chum salmon are the salmon that are most heavily produced in hatcheries. And when we look at where those chum salmon are coming from, this is looking at the breakdown by country. So Japan, here shown in the purple, they are the largest producer of hatchery chum salmon. We do have contributions from the United States and Russia, but their combined contribution is still less than that of Japan. And an important thing to note is that in Japan, chum salmon are assumed to be entirely of hatchery origin. So throughout this talk, I'll be talking about Japanese chum salmon, and just try and keep in mind those are Japanese hatchery chum salmon. So we saw that hatchery salmon production is increasing. This is looking at chum salmon abundance specifically. We have abundance in millions through time. So there's our hatchery salmon increase from about 1970 to 1990. When we look at the wild chum salmon, we don't see this huge change, except for around 1960, there's a decrease in abundance. But by 2005, wild chum salmon only accounted for 38% of total chum salmon abundance. Going back to our hatchery salmon releases, we just talked about chum salmon, which are pretty heavily produced in hatcheries, but quite a few pink salmon are produced as well. Unlike chum salmon, hatchery pink salmon only accounts for 19% of total pink salmon abundance, and we can look at where the rest of those pinks are coming from. So this is pink salmon abundance. These estimates are from Irvine and Ruggieri's 2016 paper, where abundance in millions, and on the right there, that's hatchery pink salmon production. So Alaska produces a lot of hatchery pink salmon, primarily Prince William Sound. And I think being in Alaska, we're really familiar with Prince William Sound hatchery pink production, but when you compare it to the wild pinks, it's quite small in comparison. So looking at wild pink salmon production, there are a lot of wild pinks in Alaska, mostly from southeast. And then there's a lot of pink salmon coming from Russia that are wild as well. So this analysis is looking at eastern Kamchatka pink salmon abundance. Pink salmon are the most abundant salmonid of all the Pacific salmon species, and the largest runs in the world come from the Russian Far East. So without getting too into the weeds of pink salmon life history, because they're abundant, because they have this fixed 2-year life history, they only spend 1 winter at sea, each stock is going to be abundant during an odd-numbered year or an even-numbered year, just because of spawning timing. And within a particular region, one of those brood lines can become more pronounced than another. So for example, in southeast Alaska, we saw a ton of pink salmon last year during an odd-numbered year. Forecast is pretty low for this year, which is an even-numbered year. In the Bering Sea, which is where we're focusing our analysis on, pink salmon are abundant during odd-numbered years, and the dominant stock comes from eastern Kamchatka. So this is looking at eastern Kamchatka pink salmon abundance, and you can see that there's some really dramatic differences in that pink salmon abundance between these even and odd-numbered years. And this is convenient from our perspective because it kind of provides this natural experiment to look at how pink salmon might affect other salmon species that they're overlapping with. So the overarching question in my research is how might competition in the Bering Sea affect Western Alaska chum salmon growth and subsequently maturation. My thesis is broken down into 2 chapters. Chapter 1 is a review of data on chum salmon diet and distribution in the Bering Sea. Chapter 2 is an analysis of the effects of Asian pink and chum salmon abundance on Western Alaska chum salmon growth. start with chapter 1. When I first started my project, I saw that I got to do a review, and I thought, oh, cool, that's doable. Well, it was not as straightforward as you would have thought. There's a lot of data out there, which is great. However, putting all that data together could be challenging at times. So I'm going to show you my major findings. We'll start with salmon distribution first, and we'll start with Japanese chum salmon. So Japanese chum salmon are released from hatcheries between March and May each year, and because of when they're released, they don't have a lot of time in the ocean before that first winter. So they come from Japan and they end up hanging out in the western North Pacific Ocean during that first winter at sea. They then head to the Bering Sea, where they spend their summer and fall months foraging, and then they'll spend all subsequent winters in the Gulf of Alaska. So after that first winter, they bounce back and forth between their summer feeding grounds in the Bering Sea and their overwintering grounds in the Gulf of Alaska. Western Alaska chum salmon, their natal streams are emptying right into the Bering Sea, so they're also spending their summer and fall months foraging there. And then just like Japanese chum, they head to the Gulf of Alaska where they overwinter, and will bounce back and forth between these two areas after that. Now, East Kamchatka pink salmon, here's the Kamchatka Peninsula right here. They head out to sea, and they spend their first and only winter in kind of the central North Pacific Ocean there. And then they're returning to Eastern Kamchatka. So in doing that, they're heading right back through the Bering Sea. And then just a refresher, Western Alaska chum salmon are in the Gulf of Alaska and in the Bering Sea as well. So putting it all together, thank you, Evan, for this math. We can see that there's quite a bit of overlap between these two species and among these three stocks. So we know that salmon are overlapping in time and space, but what about what they're eating? Chum and pink salmon occupy a very similar feeding niche, and Nancy Davis has collected a lot of data on Pacific salmon diets in the Bering Sea as well as the North Pacific, and she provided me with some of the data she collected from her dissertation, which was really great because we have this 10-year time series, 1991 to 2000, what are these two species eating? Before I show you, I just want you to note the prey on the left there is arranged from high-calorie, high-lipid prey items to low-calorie, low-lipid prey items. And when we look at chum salmon diets, so on average over that 10-year time period, they're eating a lot of euphausids or krill species, which are high in calories and lipids. And then chum salmon are the only Pacific salmon species with stomachs that are specially adapted to feeding on gelatinous zooplankton, which is unique. And I have overlaid jellyfish on top of the unidentified prey category as well. Often, once it gets into the stomach, it's mostly goop. So we think that those are also jellyfish species. And then pink salmon are foraging really heavily on fish, krill, and squid species, which are all very high in calories and lipids. So because pink salmon exhibit that fixed 2-year life history where they're abundant every other year, you can look at chum salmon diet during a year high and low pink salmon abundance and see if there's any changes. So during a year of low pink salmon abundance, chum and pink exhibit a 58% diet overlap, which is determined using a modified Schoner's index, the percent similarity. So when there's not very many pinks, there's a 58% overlap between chum and pink diet. I would have expected this number to increase as pink salmon abundance increases, but we actually see that it decreases to 40%, which is counterintuitive. So we can look at what they're actually eating. So during a year of low pink salmon abundance, chum salmon are eating these gelatinous zooplankton. They're also eating crustaceans, krill, euphausids, and then squid and fish. Now compare that to a year of high pink salmon abundance, and chum salmon are foraging much more heavily on these gelatinous zooplankton species, and much less so on squid, fish, and euphausids. So this is kind of drives home the point I'm trying to make, but a lot of these studies are done over a pretty short time period, which is why Nancy Davis's study is really great. So we can look at how chum salmon diet changes over that 10-year time period, and we see that this pattern still holds true. So when pink salmon abundance is low, when pink salmon abundance is high, chum salmon are eating about 19% more of those low-quality prey items and about 38% less of those high-calorie prey items. So when you're switching your diet from something that's really high in energy and lipids to something that's low in calories and lipids, that might affect your growth. So from chapter 1, we found that there's an overlap between Western Alaska chum salmon and Japanese chum salmon after that first winter at sea. They're also overlapping with Eastern Kamchatka pink salmon during odd-numbered years. And chum salmon are changing their diets when a lot of pink salmon are around by eating a lot more of these gelatinous zooplankton. All right, this is a great setup for my chapter 2, which is an analysis of the effects of Asian pink and chum salmon on Western Alaska chum salmon growth. So we have 2 objectives. Talk about objective 1 first. We wanted to ask this question: does Western Alaska chum salmon growth change with the abundance of Asian pink and chum salmon? For both of these objectives, we use retrospective scale analysis. Scale growth is proportional to fish growth and length. And if we zoom in here, I'm going to just try and explain this without rambling on too much. So salmon lay circuli down on their scales, much like rings on a tree. And you can look at the distance between these circuli, and that's actually a proxy for how much the fish is growing. So the further apart the circuli are, the faster the fish is growing. Now, during periods where fish are not growing, like the winter, for example, these circuli get really close together and create an annulus. And that's where I have these red bars. So the annulus marks the end of the growing period. So what we can do is we can measure the distance between annuli and use that as a proxy for how much the fish grew during each ocean year. So G1 is the first growth zone, and that refers to the first year they were in the ocean. G2, the second growth zone, the second year they're in the ocean, and so forth. So for objective 1, we looked at Kuskokwim chum salmon growth. We had 3,742 scale samples. The scales were collected by the Alaska Department of Fish and Game through in-river harvest, and most of the fishing effort was concentrated around Bethel, Alaska. That's where the processors are located. We have data from 1968 and then 1973 through 2013. So I was informed that this was funded by NOAA, and their sampling goal was 100 samples per year. So of that 100 samples, they tried to get 25 samples for each sex, male and female, and then for each age at which they matured. So like I said, chums spend usually 3 or 4 winters at sea. We call that age 0-3 and 0-4. So 25 samples per sex per age, 100 samples total per year. Because these fish are returning to spawn, they represent fish that survived their ocean residence. And because they're harvested in river in the Kuskokwim, they do provide some stock-specific information on temporal growth trends. So here's the Kuskokwim River, located in western Alaska. You can see in the inset on the map on the left. I did put a star where Bethel is, just because a lot of the samples came from that area. There's a photo on the bottom left of someone commercial fishing using a gill net in the Kuskokwim River. For our analysis, we used a linear mixed effects model. So we modeled the width of those growth zones, and because we don't expect overlaps in ocean distribution until after that first year at sea, we were looking at growth zone 2, 3, and 4, so the second, third, and fourth ocean year. So all of our variables were standardized, and we modeled the width of each growth zone separately. We included a factor for sex to account for sex-specific differences in growth. Male chum salmon tend to grow more than female. We included a factor to account for age, the age at which they mature. Faster growing fish tend to mature earlier. We included 2 indices of sea surface temperature, spring and summer. And then we have our Japanese hatchery chum salmon abundance and our eastern Kamchatka pink salmon abundance. Both of these abundance estimates came from Irvine and Ruggeroni's 2016 paper. We included an interaction term to account for when there's lots of Japanese chum and eastern Kamchatka pinks. And then we included this random year effect to account for shared environmental conditions that may have resulted in correlations in growth within a given year. So here's where our sea surface temperature data came from. The spring sea surface temperature came from the M2 mooring buoy in the eastern Bering Sea. It was an average of the temperature in April and May. And we included spring sea surface temperature in there because of the relationship with the date of sea ice retreat in the eastern Bering Sea and how that affects the overall net productivity of the area. And then we included our summer sea surface temperature, which was the average temperature in July and August. And that's kind of more in the central eastern Bering Sea. We have both on the shelf and off. This is an area used by chum salmon. These are our Japanese chum salmon and eastern Kamchatka pink salmon abundance estimates. So before I get into the results, I kind of want to show you what we saw overall. So this is looking at chum salmon growth separated by those 2 ages at which they mature. And we have mean growth zone width in millimeters by brood year. So G2, that's the second growth zone or the second year at sea. And we're seeing similar patterns in this population that we're seeing for chum salmon throughout their range, where overall there's just this decrease in growth during each of those growth zones we examined. So when we look at the relationship between Japanese chum salmon abundance and Western Alaska chum salmon growth, we saw a significant negative relationship. So these regression lines here are showing the relationship between mean growth zone width and increasing Japanese chum salmon abundance. These relationships were all significant, but the largest decrease in growth happened during G2 for that second growth zone. Looking at the relationship between Western Alaska chum salmon growth and eastern Kamchatka pink salmon abundance, we did not see a relationship there, and the model outputs told us that these relationships were not significant. And then talking about our spring and summer sea surface temperature indices, we also did not see a strong relationship there. Now the regression lines are kind of showing a little bit of increase or decrease, but again, these relationships were not significant. So what did we find overall with objective 1? Well, there was a significant negative relationship between Japanese hatchery chum salmon abundance and Western Alaska chum salmon growth. That relationship was strongest during the second growth zone, and we did not observe a relationship between Western Alaska chum salmon growth and eastern Kamchatka pink salmon abundance. So our second objective was asking this question: did a decrease in production of Japanese hatchery chum salmon in 2011 result in increased growth of chum salmon that were in the Bering Sea during that time? What happened in 2011? People in the southeast might remember waking up to tsunami alarms, but that was the year of the Tohoku earthquake, magnitude 9.0 earthquake that happened about 80 miles east of the Pacific side of Honshu, Japan. It's generated quite a large tsunami wave that struck this eastern side here. And NPAFC, the North Pacific Naturalist Fish Commission, kind of an international body looking at hatchery releases and catches from throughout the Pacific Rim, they reported in 2012 that 26 salmon hatcheries in Japan were destroyed as a result of the tsunami, and those hatcheries are shown here in the red dot. So we know that from our first analysis that Japanese hatchery chum salmon are affecting Western Alaska chum salmon growth. However, if you remember from earlier, the outputs from the hatcheries have been relatively stable since about 1990. So as a result of the 2011 tsunami, there was this large decrease in the amount of chum salmon that were released from hatcheries in Japan. And we wanted to see if we could use this as a way to look at chum salmon growth in the Bering Sea to see if maybe they grew more when there was less Japanese hatchery chum salmon. So our hypothesis was that decreased production of Japanese hatchery chum salmon in 2011 as a result of the tsunami resulted in increased growth for chum salmon in the Bering Sea during 2012 through 14. And I'm going to show you this conceptual diagram to kind of clue you in on how we came up with those numbers. So chum salmon would have been released from this red box here on the eastern side of the Pacific side of Honshu. They would have come out to the ocean and spent that first winter in the western North Pacific. They then would have traveled into the Bering Sea and spent their second, third, and fourth summers in the Bering Sea before returning to spawn. So as a result of the tsunami, there was much less Japanese chum in the Bering Sea during this time. So other chum salmon that were in the Bering Sea may have grown more as a result of that. So like I said, we used Bering Sea chum salmon scale samples. We had 1,845 samples. The scales were collected by NOAA observers that were deployed at sea on processors, catchers and processors. The samples came from the Bering Sea Aleutian Island walleye pollock fishery during the bee season. We used scales that were collected from July 16th through 30th for years 2001 through 2016. And all of these scales were digitized and analyzed using Image Pro. Our sampling goal was 25 samples per brood year for each sex. These fish were caught as bycatch, so there's some years we have more samples and some years we have less. But because they were collected at sea, this includes maturing and immature fish prior to their homeward migration from mixed stocks. So again, we used a linear mixed effects model. We modeled growth again separately for each growth zone. We included our factor to account for sex-specific differences. Our earthquake effect was modeled as a factor where years, where we identified years that were affected by the earthquake. We included a covariate to account for different fish ages. And then again, our spring and summer sea surface temperature indices, and our random year effect to account for shared environmental conditions. So all of our samples came, like I said, from the pollock fishery, and due to confidentiality agreements between the catchers and NOAA, we can't disclose the exact location. However, overall, the samples kind of came from this range here, mostly along that shelf break. We use the same spring and sea surface temperature indices, just over this shorter time period. And because it was a shorter time period, I'll talk about that second. Okay, so this is looking at Bering Sea chum salmon growth overall. And I would ask you not to read too much into this because this is a mixed stock where catches are driven by the pollock fishery. But what we can see is that G2, not a clear pattern there. We do see a slight decrease in growth in G3 and G4. Because we had that shorter time period, spring and summer sea surface temperature was pretty highly correlated. We ended up using spring sea surface temperature because of the relationship between the date of sea ice retreat in the eastern Bering Sea and how that affects chum salmon growth and productivity. And before I show you the results of our analysis, I want to orient you here. So this is looking at standardized growth zone width for the 3 growth zones we looked at, 2, 3, and 4. And then Japanese hatchery chum salmon abundance is shown on the x-axis here. So normal, that refers to years that were not affected by the earthquake. and then low refers to years where we saw reduced outputs. So for G2, we see that there's really no difference in growth between years of normal Japanese chum salmon abundance and low chum salmon abundance. And that pattern held through for 3 and 4 as well. So we would have expected for this growth to actually be a bit higher when there was low Japanese chum salmon abundance. The median growth is a bit lower, but again, those relationships are not significant. And why? So we didn't see any effect of decreased hatchery production on chum salmon growth. There's a few reasons that I was kind of thinking about. So maybe the magnitude of change in the reduction of Japanese chum salmon was too small to cause a significant impact on growth. We really had just this 1 year of decreased production, and so maybe that didn't carry through. It's also possible that Bering Sea chum salmon did experience increased growth, but it was counteracted by other variables that we did not account for in the analysis, such as large-scale climate indices. There was also a very large increase in the abundance of wild chum salmon over our study period. I showed you this figure earlier, looking at hatchery and wild chum salmon abundance, and we saw that in 2005, wild chums only accounted for 38% of total chum salmon abundance. But after 2005, we saw this huge increase in wild chum abundance. And by 2015, wild chums accounted for 55% of total chum salmon abundance. This data wasn't available when I started the analysis, so when I got my hands on it and plotted it, I was really surprised to see this huge increase, and I wanted to see where those fish were coming from. So again, looking at chum salmon abundance through time, we have our hatchery chum salmon abundance, and the purple there showing that a lot of those hatchery chums are coming from Japan. When we look at wild chum salmon abundance from 2005 to 2015, we see this really dramatic increase in wild Russian chum abundance. And there's less literature available on Russian chum salmon distribution, or less in English at least. But from what we do know, it suggests that Russian chum salmon are following a very similar ocean migration pattern as Japanese chum and Western Alaskan chum. And I can say with pretty high confidence they're going to be in the Bering Sea during the summer. There is a lot of data using genetic stock identification that points to that. So any effect of decreased Japanese chum salmon abundance was likely overwhelmed by this large increase in Russian chum salmon abundance. All right, putting it all together, what are some of the big picture results that we found? Well, our analysis suggested that chum salmon growth is inhibited by the abundance of conspecifics, and we looked at the relationship between Japanese chum salmon and Western Alaska chum salmon. A lot of the literature has also looked at this relationship between these two stocks. However, what I just showed you, we saw this large increase in Russian chum salmon abundance, and moving forward, it would be really useful to include that into models to see what the relationship is specifically between Russian chums and other stocks. We also saw this decrease in growth during all growth periods, but especially during the second growth period. And the second year at sea is a really important time for salmon growth. So a decrease in growth during a time when salmon should be growing a lot may result in decreased growth overall, and as a result, chum salmon may end up staying in the ocean an extra year so that they can continue to grow before they return to spawn. So decreased growth may contribute to this increased age at maturation because salmon are staying in the ocean longer. Our pink salmon effects were not as straightforward. So we saw from chapter 1 that pink salmon affect chum salmon diet by causing them to forage more heavily on gelatinous zooplankton species. However, chum salmon have stomachs that are especially adapted to digesting gelatinous zooplankton, and they're able to quickly metabolize that. However, they do not obtain as many lipids through that prey capture. Lipids are a primary energy source for salmonids and are relied upon during periods of low food availability. So it's possible that we did not see a relationship between pink salmon abundance and chum salmon growth, because changes in diet from high lipid to low lipid prey items are simply not expressed in scale growth. Moving forward, I think it would be really useful to assess changes to chum salmon body weight and lipid content and see if that relationship is more clear with pink salmon. So my last acknowledgement goes to my dad, who is no longer with us, but is definitely the sole reason I'm in fisheries today. So with that, thank you everyone for coming, and I will take any questions.
So before I forget, I want to mention that we're having our traditional off-rec potluck like we always do. We're starting it a little early because unfortunately I have a board meeting I have to get to at 5:30. So we're going to start around 4 o'clock at off-rec and bring some food to share, dogs of course, warm clothes. And so we'll turn it over to distant sites for questions before we open the floor here at Juneau. Have any questions, go ahead and speak up.
Hey Tessa, it's Peter in Fairbanks.
Hi Peter, I thought you were going to be at a meeting.
I blessedly canceled. This is more interesting. So I'm not great at forecasting, but in this case, I predicted you were going to kill it, and you did. So that's awesome. So a question. So thinking about the issue of not having a lot of contrast in the hatchery releases, except for in those events when there's like a tsunami. I wonder about using adult returns to Hokkaido hatcheries that has a lot more contrast, which suggests that there's years in which they've survived well, and so maybe using adult returns as a better predictor than hatchery releases. And what are your thoughts on that?
Yeah, that is a good point. It's kind of hard to, say exactly what trends are happening in Japan, seeing that I don't live in Japan. But from what I have read, I think Japan experienced some challenges in their returns that were independent of the tsunami. So they started seeing, for some reason, their chum salmon were not coming back. And I think that using adult returns wouldn't really get at the question we're asking, because I would guess that because the abundance of adult chum was decreasing, or the returning amount of adult chum was decreasing before the tsunami, there was some other factor that was driving those changes.
Okay. Yeah. And Jan's got a question here too.
Okay.
Can you hear me okay?
Yeah.
Okay, so I was wondering about your depiction of the abundance of Yukon, specifically Yukon chum salmon. And I guess first of all, I should clarify, is that only summer chum that you're looking at, not fall chum?
Yeah, that was just a report put out by the Department of Fish and Game looking at changes in summer chum salmon harvest on the Yukon.
Okay, yeah, I recognize that. I'm very familiar with that. But I would say that we've been having banner runs of summer chum in the Yukon for probably about that last time period that you looked at, from 2013 or 2014 on through. At least it's been really increasing. So I'm wondering about that. I mean, you characterized it as being a decline in abundance overall for Western Alaska, but I don't think that's really true overall. I mean, there might be some systems that have less, but it seems to me that they're increasing similarly to those that at the end you showed the increase in Russian chum salmon, and I wonder if you have any thoughts about what might be driving that. Even though you're seeing a decrease in growth, it seems like the abundance is, at least in the Yukon, it's going to town, and it doesn't seem to be showing signs of going back down or anything like that.
Yeah, so that's a great question, and probably not one that I can fully answer, but our From what I understand, in the Kuskokwim commercial harvest of chum salmon stopped after 2013, and that's where my data stops as a result. So I can't really answer why salmon aren't increasing without just speculating that, there's likely changes in ocean conditions that may be driving that. But we were just trying to characterize, what could have been the influence on Japanese hatchery chums for growth of Kuskokwim River chum salmon during that study period when chum salmon were in decline. And I wish that it was easier to compile all of the Western Alaska chum salmon reports, because there's just a lot of great data out there, and sometimes it can be difficult to find. But from what I have found, there are similar patterns being exhibited throughout Western Alaska, and I think it's really interesting that Yukon summer chum are kind of rebounding, and that lends optimism that these other stocks may as well. So I can't really answer why we're seeing an increase in the abundance of chum salmon, because I didn't ask that question, but rather just trying to explain this relationship between Kuskokwim chum salmon growth and these other stocks of Pinket chum.
Right, yeah, thanks, and I understand the parameters of your study, and also that the Kuskokwim run has been behaving a little bit differently than the Yukon run in this recent time period.
I'm just going to prod you a little bit on that. You might have some insight on that from all the information you learned while conducting your review in Chapter 1, thinking about what chum eat compared to other salmon.
Yeah, so they're eating. Well, so we saw that, there wasn't like a strong relationship between pink salmon abundance and chum salmon scale growth. So recent years have been warm years, and as a result, the prey may just be more abundant, or I don't know the energy content of the prey in the recent years, but there's been a lot more jellyfish or gelatinous zooplankton species, and chum salmon are able to consume those and metabolize them and allocate that energy towards growth. So maybe that could be contributing to it.
Any more questions for Fairways?
No, we're good. Good
All right,
job.
that's
Tessa.
it, Thanks, Peter. You're good?
Yeah, all good.
I was actually thinking about Ellen. I saw her little thumb sticking up. Take that as we're good. Okay, well, let's open it up here in Juneau then.
Yes.
I have a question. Did you consider including individual as a random effect to account for you got faster, slower growing?
Yeah, yes, we did. And so we ended up standardizing growth for within each growth zone, and then including that random year effect. And that was kind of our way for accounting for individual variation in growth without, throwing too many of the same variables into the equation and getting a spurious relationship. But there was a similar analysis done by Deverton et al. In Canada, and they opted with the other way of including an individual effect instead of a year effect. So that's what we were kind of trying to get at with the year effect, and then standardizing growth within each growth zone. Yes.
So jellyfish obviously probably play part of a pretty big role in this whole story. And certainly looks like chum salmon do just fine on jellyfish, and especially, it seems kind of odd that they would be the ones sort of displaced when there's lots of pink salmon around. That chum gets stuck with what we consider poor food, but they seem to be doing well. So my question actually is, have you considered looking at jellyfish? Did you consider like an index of jellyfish? I know we really only have the Eastern Bering Sea Trawl Survey Index, which may not be reflective of jellyfish on a broad scale, but have you considered that at all?
I did consider it. However, since the goal of the analysis was to look at the relationship between Japanese chums and Western Alaska chums, we really weren't trying to account for every single thing that could be driving these changes in growth. But if you were trying to account for that, I think it'd be really useful to include that in the analysis. Krista Oki is kind of trying to explain some of these patterns that we're seeing in specific salmon size at age, and there is this non-linear pattern that we're seeing, and maybe jellyfish abundance for chum salmon is explaining some of that. But yeah, since the relationship was or the analysis is trying to get at the relationship with Japanese chums and eastern Kamchatka pinks, we decided not to include that.
Continuing on the jellyfish theme, your comment about increasing amounts of gelatinous prey items, and perhaps this is associated with that rebound and some of the growth results you have. There's a lot of projections that will continue to increase with acidification, ocean acidification. Do you want to make any speculations as to what the implications are for the health of some of these chums versus pink populations?
Yeah, so there's jellyfish are definitely increasing in abundance, and we saw that even though chum salmon were foraging much more heavily on jellyfish, it wasn't affecting their scale growth, which is good for chum salmon. But jellyfish are pretty low in lipid content, and there was a study done by Kaga et al. 2013 looking at chum salmon lipid content in the Bering Sea, and they found that chum salmon lipid content was significantly lower during years of high pink salmon abundance. So while lots of jellyfish are good for chum because they can consume them, metabolize them quickly, and then allocate that energy towards growth, by consuming more of those jellyfish, they're consuming less of these high lipid prey items, and that may come into play in the winter when there's not much food around and they need to rely on those lipids as energy reserves, especially for younger chum salmon, I would think. So if younger chums are just eating a lot more jellyfish as opposed to like squid or something, that may affect their overwinter survival. And then older chum salmon may affect their reproductive potential. But I think it bodes well for chum that they do specialize on these gelatinous zooplankton species, and it's hypothesized that this trait evolved a long time ago as a way to kind of minimize that competition. Because when you look at sockeye salmon, for example, you see really dramatic differences in growth between even and odd numbered years because they're not exhibiting any variation in their diet. Ron's,
I have another one. Well, I was just thinking about that sort of recent increase in chum salmon, because you also mentioned changes in age composition, and I was wondering if you can speculate on potential relationships there.
Yeah, so when we started the project, we were hoping to also analyze changes in age class composition. There's a little bit of data that I plotted that shows like an even odd pattern in the age at which salmon mature. Chum salmon mature. However, the data isn't in a place where we can reliably analyze it, and saying anything about it, just the run reconstruction, the way the methods, is just not there yet. But hopefully in the future, that's something you can look at. But yeah, there's this increase in age at maturation that we're seeing in chum salmon, and there's research suggesting that the most recent growth period is what most heavily influences the age at which salmon mature. So they are experiencing decreases in growth during these critical time periods. I would speculate that that may result in them delaying maturation for another year, so they can continue to grow before they return to spawn, which would kind of explain this puzzle of why are chum salmon getting older.
Well, I was actually also alluding to the relationship between the abundance of the returns and their age.
Yeah, and I don't know the age composition of returns, just because there's just not a lot of good data on that. We just know that the dominant ages are after 3 and 4 winters, but there's so much variation exhibited, by stocks across like Western Alaska, even that I can't say if there's any patterns we're seeing in those changes at age. All the stats people, alright.
That's actually part of it.
Oh, okay.
So, I'm not sure your data allowed you to look at the effect of pink salmon abundance and the change in diet of chum salmon based on chum salmon age.
I didn't look at that specifically, but from thinking about chum salmon diet, I know that young chum salmon and chum salmon that are getting ready to mature eat a lot more gelatinous zooplankton than do those middle ages. So younger chums are probably not as good at competing with pink salmon or those preferred prey like fish, which there's a lot of energy that goes into capturing a fish, and pink salmon are considered to be pretty efficient foragers and competitors. So if I had to speculate, I would think that those middle age classes of chum are being more affected by the interspecific competition with pink because they're eating more of the same species, whereas chum that are maturing are eating a lot of gelatinous zooplankton, as are younger chum salmon.
So you think it's competition, not swamping by pinks?
Prey swamping?
Well, the predators, where you have so many pinks that basically no matter, you can outcompete them, but because there's, 100 to 1.
Mm-hmm. Yeah. I would speculate competition. But...
Just as a follow-up on that, wasn't there less overlap with pinks with that first year of Western Alaska chums?
Yes. Yeah, and we didn't look at G1, the first growth zone, but if you do kind of look at the patterns, G1 growth is actually increasing. And so, yeah, all the diets I've been referring to is after that first year SC, so G2 forward. But yeah, we don't expect overlaps between juvenile chum salmon in that first winter SC and other species, just because Western or Japanese chum are in the West Pacific, Eastern Chocolate chum, or they could be in the Bering Sea, but those juvenile chum are going to be much closer, much shallower than the chums that are, or the pinks that are heading back to Kamchatka.
Questions? Any more questions? Well, it's 10:59, so well timed, everybody.
Yep.
Yeah, right, no. Yeah,
especially depending on the weather, you know.
Hey Brian, I think we're gonna take like a 5-minute break or so, and then we'll reconvene for the closed door.
Okay, sounds good.
Okay, thanks.
All right.
You did awesome. You did so good. I'll be there. Merry Christmas.
There you go.
She calls it big blue, like that's really sticky clutch.
Okay.
Fun, right? I'll make it. Yeah, great.
I'm gonna give you my keys. We love this in the park.
Thank you. I'll be back in just a minute.
Plan here.
About 3 minutes ago, I told Brian we're 5-minute breaks. Go to the bathroom, get water and stuff. I think we stay in this room.
Yeah, that's what I'd heard too.
Just check out my car. Real quick. This place. Oh, it's so cold, this room.
Tessa, she's not here.
Oh, no. Let's see. Number 5.
Make me forget. I Michael.
Oh, Jerry. Yeah, we have to at least graduate 2 before we can go over 10.
Well, when you get to the point where you can't remember their names.
That's already happened to me.
Doing a finger method.
Yeah.
Do you want to move these tables? Probably move the camera so Brian can see.
Yeah, hey Brian, do you have a camera? Are you just being shy and leaving it off, or do you just not have it working?
What's the question?
Do you have a camera?
On my laptop?
Yeah.
Yeah, you want to turn that on?
Yeah, it'd be nice to be able to see you.
Change our cameras to see us.
I can't see you guys.
Got lots of snacks.
Oh, even healthy.
Yeah, I wasn't healthy ones. Well,
Okay.
I'm not prioritizing healthy food lately, so.
Yeah.
Oh, there it is.
Can we see? Now can you see us? Yeah. Only fair.
We could change the camera. There we go. The front camera.
There we go.
So it is my lunchtime, so I'm eating.
Yep.
It's okay. I brought food, but I can't share it with you, so.
All right, so just to get everybody on the same page, today is our chance to grill Tessa, make sure that we're confident in her knowledge of her thesis subject, and we could go a little more broadly into general fisheries things if you want also, and then to decide whether she passed her defense or not. This is not the same as signing off on the thesis itself. That will happen at a later date. So there's still plenty of time to offer edits, comments, suggestions on the written document. So this isn't signing off altogether on Tessa's master's degree as the defense today. So.
I did reread my thesis yesterday, and it's amazing what 2 weeks of not reading it does for your brain.
You can see things again.
Yeah. Oh, I didn't. I have that sentence in there twice. That's not right. My important implications needs to change. It's a great phrase, you know.
Yeah.
Not when it's overused.
It's becoming one of those empty words, phrases. Right. So I think at the end we'll boot Tessa out of the room. But for now, unless people would like to talk amongst the committee without Tessa present, we could do that too. But if nobody has a strong feeling to do that, we could just go into questions also.
Good.
Okay, let's dive in. So let's go around. Anybody have a pressing question they want to ask or follow up on? Or...
I can start.
Okay.
So when it comes down to trying to explain this discrepancy between the effect that pink salmon have on the chum salmon diet and not seeing anything in the growth, you said a couple of things. You said that maybe they could have an effect on lipid content of the chum, and it wouldn't show up in the scale growth. And then you also had a reference that said that there was chum salmon had lower lipid content when pink salmon were abundant. My question is kind of a biology question because, you know, I don't know that much about physiology, but I know that there's not always a 1-to-1 ratio between what you eat and what your body composition is.
Right.
You know, can chum salmon synthesize the lipids that they need in a gelatinous diet?
I just don't think they're getting many lipids in a gelatinous diet, and I guess that was the point I was trying to make is if you're eating something that's really high in lipids, you can kind of make a decision: am I going to grow? Am I going to store it? Am I going to invest this into egg or gamete formation? But these jellyfish, they're just not high in lipids, so anything that they do obtain, it seems like they're allocating it towards growth. And I don't know a ton about chum salmon physiology, and Brian might be able to correct me if I'm saying something wrong, but I just think it's that they're not acquiring many lipids by eating gelatinous zooplankton. Probably eating some, but from the diet data I've seen,
Yeah, my question is, I guess, is can a chum salmon accumulate a lot of fat on a diet that's low in fat, maybe high in calories?
As Americans are.
Yeah.
I had the same question actually. Yeah.
Well, okay, can you repeat the question?
My question is whether, just because you're eating a diet that's low in lipids, does that mean you can't accumulate a lot of lipids, a lot of fat reserves in your body?
I think you could, yeah, and it's likely, there's more than one factor coming into play here. So if you're not able to eat thousands, for example, but you're able to eat a ton of jellyfish, well, there's clearly an advantage to doing that because chum salmon that are maturing specifically are targeting these gelatinous zooplankton. So I guess if you're able to consume enough and quickly metabolize that, yeah, you can pack that on. And if we're seeing that more with older chum salmon, that's likely what they're doing is foraging really heavily on gelatinous zooplankton as they're getting ready to mature, and then using those lipids and energy that they've obtained for whatever when they're homing, traveling back to their spawning stream. But for younger chum salmon, their relationship might be different, just because they need to grow so they can avoid the size selective mortality, but at the same time they need to be able to survive through the winter. So yes, to answer your question, I think that you can obtain lipids by eating enough gelatinous zooplankton, especially if there's a lot around.
Yeah.
And they're easier to capture than a fish, for example.
So, Brian, I just noticed it said meeting's going to end in 5 minutes. I think what's going to happen is this public defense meeting will end and then the closed door will start. So you might have to go through the same reconnection process.
Okay.
Sorry to interrupt. Abby told me she was extending it. So.
Why don't you check with Chris? Gabby got called away by an emergency.
Oh, okay. Yeah, because that makes me think it's not going to reconnect. Okay.
Yeah.
So these warriors are supposed to be shipped towards smaller gelatinous zooplankton, as far as jellyfish, body size smaller. I'm wondering if that's an advantage for chum salmon if they're more able to eat the smaller ones better than the larger ones.
Yeah, that'd be interesting.
Seeing those in more warm years even down off California, it's been this massive trend.
Yeah, that was making me think about Curry's, the chum salmon kind of came out as the strongest correlate of the Chinook productivity in that life cycle model that you guys did. And I was like, oh, well, maybe years that are just really good for chum salmon are just, trophically representative of years that are not good for Chinook salmon. And so maybe there's actually no causal connection there, but maybe it is actually not just a correlation of time series kind of issue.
Yeah, it could be. I just, that Hokkaido chum salmon time series is really problematic. Does that?
Yeah. But, I'm going to ask her about this too, but when she shows the Rougeroni and Irvine, I can't remember if they're estimating the number of maturing fish out in the North Pacific or just all ages.
I thought returns. Isn't that what they were calculating?
I don't remember. Somebody did.
It's more complicated than that.
I use this time series of age composition to calculate the number of fish in certain years in the ocean using returns and age composition time series, but I don't know if they did that.
Yeah.
I thought they just did returns.
Brian, do you know?
What's the question?
Oh, the Irvin and Rigeroni papers, are they estimating the number of maturing fish out in the North Pacific, or like all age classes?
Yeah, I don't know.
Okay. Hopefully Tessa does.
Pretty
I
sure.
feel like I've asked her this before.
No, it's Peterman Papers was trying to estimate total biomass.
Use their 2010.
Your call will be disconnected.